Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and with me as always is...
Robert Moore.
Robert, this is episode number 4 of our second season.
Yeah.
And for those
Cruising
who may be...
right along.
Sorry, go ahead.
Cruising right along.
Cruising along. And for those of you who may be new to our podcast, we are doing this live on the campus of the University of North Dakota here in Grand Forks, North Dakota. We do have a live chat feature, so you have any comments or questions throughout the podcast, please feel free to use that feature. And also as a disclaimer, anything that Robert and I say are our own personal opinions and not necessarily those of anyone else or any other institution, or organization, or government, or country, or planet, or solar system, or galaxy, or the universe as a whole.
I don't know about that.
Did I cover everything?
Yeah, I think you covered everything, but I do speak for Mars. Oh, wait, no. You're not supposed to know that. Forget that.
Now, on this podcast, we like to cover various things that's happening, current events related to physics, science,
in
general. And there's always lots of things that seems to be going on related to astronomy. So we end up always focusing on that one way or the other. And that includes this week, right?
I don't know. It could have something to do with a couple of astronomers doing the show. So where do we look?
Well, there's things happening all the time. That's a good thing. I'm not complaining.
Oh, yeah. No, I agree.
Right? So, but it's hard if you're writing a textbook.
Okay, yes.
Right? So you're a writer, Robert.
Yeah.
Right? So you can share with our audience, imagine that you were trying to write a nonfiction book on a topic like, I don't know, astronomy?
Yeah.
And things keep changing on you because of new discovery and new observations. So you got to go back and keep changing and updating. At some point, you're going to get fed up, aren't you?
No. At some point, you just say, I work with the best information I have at this time. You get the book finished. Then you tweak if you want to.
So you could put in a disclaimer to say, this is all the information that I know of as of January the 30th, year 2024.
Right.
And even if something dramatic happened the day after, well, just too bad, that'll be in the second edition of the book.
Right, that's in the second edition or the foreword or something like that. Something you get to put in there before it goes to print.
Right, exactly. Now, we noticed that in the last several years, there's been a lot more attention in recent times, if you like, on the moon itself.
Right. Yes.
So way back, even before my time, way back, the moon was obviously central at people's attention. And that really was coming out of the beginning or the dawn of the space age.
Right.
You could think of competing governments, for example, the United States and the Soviet Union at the time. One of the things you could say is we look around and say, okay, where can we go to kind of demonstrate our prowess in space exploration? So fortunately, we have the moon. And the moon's not that far away. It's just a few days away, with the technology that existed back in the 60s. And even today, it's about the same, in that sense. And one often wonders, if we didn't have the moon, what would have been like the objective to show, like to demonstrate, if you like, that one country is a superpower over the other? The moon was an obvious target, right? Who's the first to get to the moon, right? And you could go there by robots, of course. Even if you crash landed on the moon, you made it to the moon. But you could also go a step further and say, okay, who's the first country who's going to land people on the moon and then return them safely to the Earth? And that's, of course, the announcement by Kennedy in, was that 61 or something like that?
Something like that.
So the early 60s. But imagine, like I said, there is no moon.
I don't know what you do, but that makes an interesting what if. What would you do?
Would it have been such that we be on Mars now? Would Mars have been like the target? 'Cause obviously, with the space age and the investigation of Venus, we knew that was no way that you can land people on Venus. We can't even do it today with technology. It'd be very difficult. But going to Mars may have been the way. So we might have been in a situation where instead of doing it at the end of the decade, being the 60s at the time, doing it at the end of 20-year period.
Well, I mean,
going to Mars.
Yeah, I'm still sitting here going, it'd be a big task for us to pull off a trip to Mars with people today, much less in the 60s and 70s. I don't know that it wouldn't be like, thinking about life under the ice surface of Europa. Any life there would never see the stars at all. So would they be directed outward in any way, shape, form, or fashion?
I would say probably not. Well, think of dolphins.
Right.
Dolphins are highly intelligent creatures here on the earth. So if dolphins represented, if you like, the peak of the pyramid,
Right.
would they have any interest at all what was going on beyond where they live in their local environment?
Considering they get everything they need without the use of tools or anything else, I doubt it. You know, why would they?
So just because we're going down a little rabbit hole, but just because there's like an intelligent life form on some other planet doesn't necessarily mean they're spacefaring nation
Right.
or spacefaring civilization.
Absolutely. I just had never thought about that angle of things. But yeah, if there's nothing there to push them, to drive them, to make them say, hey, what is out there?
The other thing too you can
You
think
know?
of, imagine we lived on a planet that wasn't like the Earth, that was
Mhm.
more massive and even the same size, it was denser.
The gravity would keep us from getting off.
That's what I'm getting at, that we,
Yeah.
with present technology, would not be sufficient enough to reach escape velocity.
Right.
So that's another thing you could think of.
Tyranny of the rocket equation,
Yeah.
folks.
But if there wasn't a destination like the moon to go to, you can imagine that things would have been very different.
Why bother? You know,
Yeah. Or, like I said, you have to really push things. And so you brought up the fact, and can we have gone to Mars? Well, I'm thinking of Skylab,
Right.
where we used one of the last Saturn V's, right? There's, I think, 3 of them were put in museums,
Mm-hmm.
right? Or at least there's one at Kennedy Space Center, there's one down in Houston. And I know we used one for the Skylab mission, so there was
Right.
so there were 3 left over from the Apollo project, right? Because we went to Apollo 17, there were supposed to be 18, 19, and 20.
Right.
So one of them was used to launch Skylab, and the other 2 became museum pieces. But if you put up a Skylab-like object in space,
Mm-hmm.
and you outfit it for the long journey to Mars, and then be able to attach, sufficient booster power to do the long journey. I mean, somebody would volunteer for that even today. I mean,
True.
people volunteer to go to Mars, remember, and
point.
never come back, right?
True.
Wasn't
Fair
there a
point.
group was it from the Netherlands that
Yeah.
asked for people to sign up a few years back to
I
see?
don't remember which country, but yeah. And
Yeah.
It's like people were willing to sign up.
So-
I don't get it.
So there'll be definitely astronauts that would have been willing to go on board a modified Saturn V Skylab type of situation to do that long journey to Mars and hopefully back.
I don't think they would have made it there, much less back.
Well,
all
even
it
if
would
they
take
made
is-
it there, we wouldn't have made it by the end of the 60s.
Right. I mean,
But certainly by the end of
Yeah.
the 70s, technology would have, if you put the
True.
money into it, would have advanced far enough, we would have made it to Mars and
Right.
back. In some sense, that might have pushed space exploration of the solar system a lot further along than what had actually happened by going
Right.
to the moon.
well, let's face facts. The reality of the situation, it was a political stunt and was made to do flag waving. You know, the science done was really just secondary.
Definitely was. In fact, if you look at the history of the Apollo program, a lot of the science really happened near the end of the
Near the end.
project, right?
Mhm.
When the last couple landings had a lot more instrumentation, and they had the extended lunar module that allowed them to stay a lot longer on the surface
Right.
and therefore perform more science. So I think if we would have had, a much lot of money left to spend, and you managed to go to Apollo, I don't know, 30 or something like that,
Right.
you can imagine being a huge amount of science that would have
Oh,
been done. We'd be sending scientists mostly.
Yeah.
We did send up one scientist, right?
Right.
And so that a
Geologist
geologist,
at
right? So probably maybe 2 out of the 3
Mm-hmm.
of the, but then you need a pilot, so you try to get scientist / pilot, right? To be
Right.
able to land
Well, you
on
do
the
like we
surface.
did with the shuttle cruise there towards
Yeah.
the end of that program.
Yeah.
You know, where people were cross-trained and everything. And I ain't gonna lie, that's almost certainly what we'll do when we send people to Mars, is they'll all be double and triple cross-trained.
Well, the other thing, you're thinking of mission specialists, right, on the
Right.
space shuttle. Yeah, the other thing we could have done is design a much larger landing craft to go to the
Mhm.
moon eventually. So instead of having just 2 landing on the surface, maybe we could bring down 5,
Right.
one being a pilot, one being a backup pilot, and then the other ones all being pure scientists, like geologists, for example,
Yeah.
to explore
Yeah.
the surface of the moon.
I mean, absolutely.
Yeah.
You know?
But of course, that's not what happened. But in the interest of going back to the moon kind of went away. So in the 70s, when our attention focused on other things, I'm talking about not just the United States, but the world as a whole, going back to the moon was kind of, no, like, we did that, let's move on,
Why do
right?
we need to do that?
Yeah.
In fact, there's still some of that attitude today.
There definitely
Why aren't we
is.
landing people on an asteroid so we can start developing this mining technologies
Yeah,
and
why?
things like that?
Yeah, why do we want to go back to the moon? We've already done that. Let's move
Been
on.
there,
But
done
there's
that.
still a lot
Right.
of stuff that needs to be done.
Yep.
And of course, because the moon is so close, it's a forward base of operation, if you
Right.
like, of going elsewhere in the solar system.
And if we ever get fusion energy, it's a prime source of fuel for any rockets or anything. So
I mean, going to Mars, I mean, if any trouble ever happened, it's a multi-month journey to get back.
Yep.
And that depends on the alignment of Mars and the Earth at the time.
It may not be possible at all.
Well,
if
yeah,
they're on
and-
opposite sides of the sun.
Yeah, and so what are we going to do? Not go with humans and wait until technology advances so the journey to Mars only takes a few days rather than
Right.
several months? I mean, you got to think about those things, right?
Absolutely. And this is all part of the planning, folks.
Yeah.
These types of discussions go out at just about every such meeting I've ever been at. So.
Well, now with the development of the Artemis project,
Mm-hmm.
so the United States has returned to the moon. Of course, they're trying to get international partners to lessen the cost, to bring everybody on board. So there's
It
like,
should be.
yeah, so the moon now is becoming a target once again.
Mm-hmm.
I mean, there's different countries, not just the United States, but there's other countries around the world,
Let's
like
see.
India and
India,
China and Japan,
China.
landing vehicles
Yep.
on the moon. And eventually, of course, that's just a forerunner to eventually landing humans on the moon
Right.
by those countries. And so one of the things that happened recently, which is why we're mentioning it today, if you want to turn to our first slide, Robert, is a unmanned probe that Japan landed on the moon a few days ago. The SLIM mission.
Slim.
So it sounds like this is it wants to go on a diet or something. So it stands for Smart Lander, as you see there, for Investigating Moon, SLIM. Okay. Now it was launched back on September the 7th of this year. So I like missions to the moon. You know why? Like, well, there's many reasons, but here's one reason.
It's fast.
Yeah, I don't have to wait 10 years for the probe to
Right.
get to the destination, right? I only
Right.
have to wait, usually a few weeks or a few months, right?
Mhm.
Depending on what the trajectory is to get there.
Right.
And you remember back in, I guess it was back in the 70s when people were planning these journeys to go on to various planets like the Voyager missions, Voyager 1 and
Right.
2. And they, in some sense, that was the optimal type of trajectories, right? You get the gravity boost from Jupiter and from Saturn and Uranus to go on, at least for Voyager 2, to eventually fly by Neptune.
Unlike Star Trek's, optimistic view of things, there weren't any plans for Voyager 3, 4, much less a Voyager 10.
In fact, the initial program of Voyager, if you read about a little bit about the history, it went through a bunch of different incarnations, if you like. One of them was just one probe.
Mm-hmm.
And NASA strongly argued that because of the long journey that this probe would take, and this had never been done really before, you had Pioneer 10 and 11,
Right.
but I mean, there was a lot of sophisticated science experiments on board these robots, essentially, Voyager 1 and 2, that minimum that we should send would be Voyager, like 2 of them, right?
Mhm.
So, which became Voyager 1 and 2. And the other was that Titan was a major target of opportunity. They wanted to study Titan.
Right.
And the reason for that is because Titan has an atmosphere, and we knew it at the time before the Voyagers were launched. And people speculate, like some scientists speculate, the conditions may be right on that planet given a greenhouse effect that would be warm enough to maybe that life would have formed and still be there today on the surface. Okay. Now, it turned out to be much colder
Right.
than what they suspected. Okay?
Right.
But there were some suggestions that it was a lot warmer than what
Okay.
it turned out to
Okay.
be. But if you want a good view of Titan, that trajectory in the 70s, when they launched, means that you couldn't go on to Uranus and Neptune. If you flew
Right.
close to Titan, that was the end, essentially, of the planets in our solar system. You wouldn't be able to, have
Right.
any close encounters with anything else at the time. And so it was thought that if we send 2, the first one will send very close to Titan, as close as we can, and that would be the last of the visits that it would do. So it would go to Jupiter and Saturn, that would be the end. And then the next spacecraft will make it fly by Titan a lot further away. And then it would actually be able to go on to Uranus and Neptune.
Okay.
In fact, that's the only reason why we have close encounter views of Uranus and Neptune is because of the flyby Voyager
Not that
2.
we got too close to either, but
Yeah, so
a lot closer than anything else.
and Voyager 2 flew by Uranus in January of '86, and why I know that is because it was happening just at the time when the Challenger blew up,
Okay.
which is,
See, I didn't remember that relationship.
yeah, I mean, well, I remember it because I read about it, and we just
Yeah.
gone through the anniversary of Challenger, so there's some
okay.
articles out there talking about including what was going on at the time in space, history, and that included the flyby Uranus. So it's like everybody was at JPL, all the space reporters, waiting for the close encounter views of Uranus. And then when Challenger happened, all those reporters dumped out and immediately went to Kennedy Space Center
And that would be
in Houston,
why
Texas.
It was kind of muted, not understandably, justifiably.
Yeah. So then a few years later, in '89, that's when Voyager 2 flew by Neptune.
Right.
And of course, that was a big, thing because at the time it was the first time we had a close view of Neptune and especially its moon Triton. And there was really nothing else going on, so it was the centerpiece of attention.
Or we thought.
Right. But it was the centerpiece of attention at the time.
Right.
In fact, that was our last view of Neptune, close encounter like that. So when are we going to have another one? Well, it could be, long after we pass away, right?
Absolutely,
I mean, it could be 40 years from now for all we know.
I don't think anything is on this. Oh, no, that's right. They're talking about it.
They're talking about, but the real talk now is on a flyby of Uranus. And not only flyby, I shouldn't say a flyby, we're talking about an orbiter mission. In fact, that orbital mission, so a probe will go in orbit around Uranus and will also take another probe that will go down into the atmosphere like we did with Jupiter and Saturn, right? We put Cassini in the atmosphere, right? At Jupiter, we have Galileo went in, but we had a probe on Galileo that went in first, right?
Right.
So we'll do that with Uranus. We'll send in a specially designed probe to sample the atmosphere and its pressure and density and composition, those sort of things. So that would be you need an orbital mission to do it. It's a little more difficult. Flybys are easy. Why? Because you don't need to slow down, you see, and go into orbit. You can just fly by, take your data, and then on you go, right?
You got to be pretty precise to get a braking orbit that'll pull you back in.
Well, what it means, when you think about it, is you have to carry more mass. And because of that, you need a bigger rocket, right? More power to get there. Or you take a much longer route.
Okay.
So you can think of using like ion propulsion engines, but it may take you a long, long time to get there, right? Depending on how your path is, your trajectory.
For those that may not have heard, an ion engine is a wonderful thing. It produces a lot of thrust per amount of fuel, per mass of fuel it uses. But we're still talking about a thrust that's about the weight of a piece of paper held in your hand.
Right, so it's very efficient.
Very efficient, but very low actual force behind it.
Yeah, so your change in velocity for those physics people, your acceleration is very, very tiny. But if you thrust continuously for thousands of hours, that builds up and builds up and builds up.
Yep.
So you can build up your velocity, but it just takes a lot of time.
It takes a long time.
But it's very efficient. It'll get you there eventually.
But you know what you have between Jupiter and the rest of the outer planets? A lot of time. A lot of space to cover.
And when you think if you're a planetary scientist, right, and your whole career, it may be starting in graduate school, is to work on one of these missions to get it going. You launch it by the time you become, a postdoc, let's say. By the time it gets there, you might be near depending on where you're going, you might be near the end of your career as an academic, right? It's academia, as a full professor somewhere.
So they're starting to make it as part of your job is to train your replacement, essentially.
Yeah. So that's the unfortunate. It'd be nice when technology gets to the point where we can get to these destinations a lot faster.
Oh, yeah.
Less than a year, preferably.
That's why I mentioned fusion.
Yeah, less than a year, right? If you could get through Uranus, imagine that in less than a year.
That would be nice.
Talk about the advancement.
Especially if you could then brake hard enough to pull into orbit.
Yeah, exactly. So you're talking about a lot of power. Well, at that point, aren't we ready to send robots to the nearest star to the sun?
Oh, absolutely.
Yeah,
absolutely.
Proxima Centauri, here we come.
There's our next flyby.
Now, the moon itself is, like we mentioned, has become a recent target because of the Artemis program and others. People have developed a technology where, hey, we're ready to go and do something here.
Right.
Let's hit the moon because the destination is relatively close. We can get there. So this is one recent attempt at this, and Japan landing an unmanned probe then on the surface of the moon just a couple days ago. It wasn't that long ago.
Mm-mm.
As you see there, as I mentioned, it was launched in September, and it went into orbit of the moon back on Christmas Day of 23. And they waited a while, check it out and get it prepared before they decide to have it actually try to land on the moon itself. So when the landing of the moon on the moon actually happened, and it's all done by robots, of course, there was a little bit of a problem. This is all controlled by computers. In fact, I was actually watching the day when it was landing there the other week, and you could see, they got all the fancy graphs, and you could see the probe, the icon, if you like, right on the graph as it gets closer and closer, and the height above the surface of the moon is decreasing and it's going down and closer and closer and closer and closer. And all of a sudden, right near the end, just at the point where the craft was supposed to softly touch down on the moon, anyone who was following that, and of course you can go look at it on YouTube or whatever and replay it right near the end, you'll see that the icon they were used to represent the SLIM mission, right, the object that was landing, it actually flipped upside down. And I thought, well, that's kind of bizarre why they did that. It must be just because it's over with, and they didn't put anything there that matched reality at that moment, right? They kind of just moved the icon away. It's in its landing spot. Forget about it. But that actually was telling us something very important, because the data that's being relayed back to Earth was giving you the orientation of the spacecraft relative to the surface of the moon. That include, of course, the height information. So if you go to the next slide, Robert, and look at the image on the right, the object actually landed on the moon upside down. I think this is the first time this has happened where the vehicle has survived and be able to get pictures from the lunar surface showing you the object upside down. Now, the only reason why we have this image on the right is because there were some probes on board, some, if you like, rovers.
Oh,
right?
okay.
There was one that hopped,
okay,
and one that rolled like a ball on the surface. And if you want to call them micro probes or whatever you want to call them, as when they were ejected finally into the surface, one of them, they have cameras on board. They looked back and took a picture of the main spacecraft, and we got photographic evidence, as you see there on the right, that the spacecraft, yes, indeed, landed on its roof, upside down.
Landed intact.
But it didn't hit hard. So what happened to it, as far as I understand, is one of the thrusters quit working just before it softly touched down. And because there were multiple thrusters on it, that caused the vehicle to flip around upside down, and then it touched down at a very gentle rate of descent. So it wasn't hard enough. And don't forget, the moon has 1/6 the gravity of the Earth.
Right.
So it touched down softly on its roof. So it didn't destroy it. Now, the problem here is that there are solar panels on this lander, and the solar panels are not all the way around the surface, like covering it.
Oops.
Yeah, so when it landed, it was programmed to land in a certain orientation so that the solar panels were pointed towards the sun. Unfortunately, the solar panel was pointed away from the sun. So the vehicle had a battery on board, and the battery lasted for a little over 2 hours before it finally failed. So it went quiet. So in those little over 2 hours, the Japanese scientists on Earth, of course, were doing everything they could to rush through the procedures, I could imagine, trying to collect data. You take images, launch those probes and get them out there, all of this kind of stuff before the battery died. Now, what happened was earlier this week, in fact, on Sunday, it was announced that Japan reacquired the signal from this lander. Why? Because the sun moved. And the sun now was illuminating the solar panel, and that generated power enough that it started communicating with the Earth, believe it or not.
Wow.
But that only lasts for a while. In fact, I've heard, and I don't know if it's true or not, but I heard that it's only good till about Thursday or so, and then the sun is in a position where it's not going to fall the sunlight on the solar panel. So then, the battery will be dead at some point. And the way it works on the moon, so the moon takes a little over 28 days to go around the Earth once. So at any sort of place on the location of the moon, other than the extreme poles, let's say, right down inside of a crater or something. Let's say you're on the equator of the moon itself. you would, if you were standing there, you would notice that the sun rises in the east, just like it does here on the Earth. But it takes 2 weeks for the sun to go from sunrise to sunset. So a day, quote unquote, on the moon is 2 of our weeks.
Okay.
Now, the other thing is, once the sun sets, it takes 2 weeks before it rises again. So the night on the moon is 2 weeks long. So a whole day then is 4 weeks roughly.
So what you're saying is it's a month for one complete cycle?
Yeah,
Wow.
exactly. And so imagine in the future when astronauts stay on the moon for a long period of time, you got to get used to that, right? And maybe you can, right? You go to sleep. I mean, there's lots of people who do shift work, right? So they sleep when the sun is up, right?
Right.
You just have the right environment where all the windows are blocked and stuff that you can get to sleep. And that same thing would happen on the moon. So imagine a base built on the moon like we have bases in the Antarctic, right? Moon Base Alpha, for those of Space 1999 fans. And you can watch that on Tubi and other places, by the way, for free. You don't have to go buy it now. It's available. So if you if you're at a base on the moon, then yeah, you can go outside and explore, which is the best time to go out so you can see with natural light from the sun.
Right.
You'd have 2 weeks to explore, but then you suffer for 2 weeks where it's nighttime. But then that's when you can do your astronomy, right? You can have Now you can do astronomy during the daytime. You just can't look near the sun.
Right.
Right? There's no atmosphere on the moon to think about, so you're not getting reflected sunlight to cause the blue sky. You can see all the stars in the sky in the daytime. It's just that when you look towards the sun is going to be so bright, you don't want to point your telescopes near there. Right?
Can I mention something? If
Yeah.
it was your eye, you would actually see stars on the day side of the moon. Cameras, however, do not have the dynamic range of your eyeball to be able to see stars when you're taking a non-saturated picture of the moon's surface. But your eye could pull it off.
And I know where you're going with this, Robert.
Why? I would have someplace on
Robert, are you part of that club?
No, I am not.
There's a club out there, folks. And that club, to get in, you have to swear
That it never happened.
that the Apollo missions never happened, that we never landed on the moon.
Yeah.
And one of the reasons for it is when they took pictures,
There are no stars.
there are no stars. It must have been somewhere in a warehouse. Have you ever seen Capricorn 1?
No?
That's a movie where they fake. O.J. Simpson is in that movie.
Huh.
I don't think it's from the 80s, I'm not mistaken, where they faked the landing on Mars.
Okay.
And then the the vehicle, when it was coming back to Earth, they were going to put the astronauts in it when it landed before people got there.
Right.
Secret covert operation. But what happened was the capsule burned up, so they had the theme of the movie was they had to kill these 3 guys because technically they died. So they're running around essentially chasing these guys in the desert area, and they killed 2 of the 3, and the 3rd guy got away and actually showed up I'm spoiling the movie, aren't I? He showed up at his funeral at the end of the movie. And that's how the movie ends. So then the people who were involved, of course, were thrown in jail, for killing
Right.
those other 2 astronauts. But they faked the Mars landing, and it was based in part on the fact that some people speculate that we faked the moon landing. They can't
Right.
believe we went to the moon, and that was actually common even in the times when it was happening.
Yes. But then again, at the time it was happening, there were still people around who didn't believe in airplanes. So
Well, word of advice, Robert: don't tell Buzz Aldrin he never went to the moon.
no, he clocked the crap out of somebody who did that.
Yeah, so you got to be careful what you say.
Yeah,
like that.
I'll agree.
Anyway, so now the image that's on the left here actually shows, this is a demonstration of how sophisticated software is and instrumentation that we can send to places like the moon. So what it's doing is it's showing you a target landing site, and then the software scans around for hazardous objects, and it's programmed to adjust its targeting so it lands in a safe area. If you like, it's what essentially Neil Armstrong did on Apollo 11, right?
Right.
Because of a computer problem, computer was overloaded, and there was different alerts that were going on
Right.
at the time. If you're into that and looking at the landing, right, there are different alerts that was going at the time, and it was a overloaded computer, it turned out, trying to process too much information.
Too much information, yeah.
And computer technology back in those days, well, your cell phone has way more computing power than what they were using on the Apollo spacecraft, right, on board.
So you get 5 alarms going, and the computer shuts down, says, "Whoop, I'm done."
Yeah. So what happened essentially was the computer was driving the lunar module to an area that was not safe to land. And Neil Armstrong and Buzz Aldrin knew that. So Neil Armstrong, who was in control, he took manual control of the lunar module and he flew to an area where he found that was safe to land.
Yep.
Now, one of the things with the lunar module, I forget the exact number, you can't be tilted by so many degrees. If you are more than that, you can't get off the surface.
Right.
You know, there's a lot of these issues that you have to watch out for. You don't want to land and flip it upside down inside of a massive crater
or
hit the wall of
sideways,
all this
yeah.
stuff. So you got to be very, very careful here. And so it's like this is already built in now into the software, into the technology where this probe could look down and figure out where is the safe place to land. So there's the initial target landing site. There is another area that you can see there that's sort of a safe area to land. And then it actually landed a little ways, the actual landing site, at least the estimated landing site, is a little off from that. Okay, and you can see, you'd wonder if it bounced when it hit, but it doesn't look like it. There's no structural damage visible to the top of that probe.
I don't see any fragments or anything.
No,
like that
so if it would have hit hard enough to bounce, I think it would have been game over, right? It
Right.
wouldn't have been able to communicate with Earth after it landed.
I also, looking at it, would think that if it had bounced, it would have landed over on its, fallen over on its side.
On its side, yeah. So you can see the actual landing site. It's about 55 meters off to the targeted landing site. But this is like the adjustments you can do in near time, right?
Mm-hmm.
You know, as you're proceeding to do soft landing on the moon itself. It's quite incredible when you think about it. So the moral of the story is never give up.
Never surrender.
You know, they always, you think the mission is over and NASA says, well, or some people have said, oh, don't listen to it, let's do something else. Like, no, let's keep listening. The next opportunity, maybe, you never know, it might start broadcasting again. And that's exactly what happened with this probe, right? So we'll see how long it lasts. The other hope is, as we were talking about the day and night cycle, some people figure that it won't last throughout the night because that's 2 weeks long, right? It gets
and
cold.
Gets too cold.
Yeah, but some scientists from Japan are speculating, no, it may make it through the night. So they're going to actually listen for it to see if it's going to reestablish communication again after the 2 week night. You never know, right?
You've got the money that you put inside to pay for the mission for so long. Why not have at least some of the people still listening for it?
Yeah, the other thing would be nice if they had technology that you're testing, like the cold weather technology.
Right.
Right, to see if it could survive a night on the moon. I mean, why not?
Why not?
I mean, yeah. So, well, there's going to be some more interesting, hopefully, information coming out that we can maybe update people, in several weeks from now to see if it did survive the lunar night. Now, the other thing, talking about advanced technology and landing on objects beyond the Earth, our next sort of news that came out recently since our last podcast is news about Ingenuity. Now, for those who don't know or forgot, Ingenuity is a helicopter, essentially, that landed on Mars with the Perseverance rover way back in February of 2021. Now, this helicopter, number one, helicopters can fly on the surface of Mars. Right. They cannot fly on the surface of the moon. So if somebody proposes to you that, hey, would you like to be part of this proposal? Well, what are you proposing? We are proposing building a helicopter and sending it to the moon. Run away.
Run away.
Because the moon doesn't have an atmosphere. Now, it has a trace amount of sodium atoms that come off, but it has no atmosphere. You can't fly a helicopter on the surface of the moon.
It's nothing that I would call an atmosphere.
Yeah, well, that's it. So a helicopter is just not going to work, right? You need something like rocket thrusters to get off the surface of the moon. So for Mars, it does have a bit of an atmosphere. It's certainly not like our atmosphere. The pressure is extremely low. You would not survive on its surface without a spacesuit. Right. And a good way of thinking about it, if you had a pan of water and you placed it on the surface of Mars, that water would explosively evaporate because of the extreme low pressure. It would immediately go to the gas phase.
Gas phase, yeah.
So you don't want that happening, to the blood in your body, right?
Right.
So, yeah. But it does have an atmosphere. There's a little bit of an atmosphere. In fact, technology has advanced now to the point, especially when you think of drone technology and all this kind of stuff, that we can actually build a helicopter, a little small, tiny helicopter, and the image of it sitting on the surface of Mars is the one that you see on the right, by the way. We can build a helicopter that actually can fly. Now, notice it has two propellers, but it rotates a lot differently than the typical helicopter on the Earth.
They counter-rotate. One blade spins in one direction, the other spins in, on the opposite direction. So, and I looked up a little bit of information. They spin at roughly 2,700 RPM. So to give you a comparison, a helicopter's rotor here on Earth spins at about 300. So we're talking several times faster that these blades have to spin, and there have to be two of them. And the reason they counterspin is so that the air isn't sucked out of one by the other. And so, with it counter-rotating, it also is a matter of torque. If you just have one that starts spinning, head over tail, whereas with two, the torques cancel out and you keep it upright.
So you have better stability with the two.
Better stability with two.
With counter-rotating.
Yep.
And so the number I like is the difference in the number of revolutions it makes per minute.
Right.
So on Earth, a typical helicopter will go around, make a circle 300 times in 1 minute.
In 1 minute.
And this is what, 2,700?
2,700.
2,700 times in 1 minute. And that
Right.
difference is because of the much thinner atmosphere on Mars compared to the Earth itself.
Absolutely. I thought it had to be faster than that because, Mars is close to being a vacuum. Your vacuum cleaner in your house is less of a vacuum than Mars's atmosphere. But there's enough.
So if you sent an object like this to the surface of Venus, it has a much thicker atmosphere than we have here on Earth, than one would imagine, and it has roughly the same mass, so gravity is going to be the same as Earth. So it could spin a lot slower. It just have to develop the electronics that can survive the scorching heat of the surface of Venus.
And a material that'll survive the harsh conditions of that atmosphere, with it being a lot of sulfur compounds like hydrogen sulfide and sulfuric acid.
Yeah, so you don't want to be standing on the surface of Venus without a spacesuit either.
Right.
Extreme pressure, extreme heat, and then the acid in the air, right?
Right.
Be attacking you immediately, right? You feel it.
Yep.
Yeah, not good.
Especially since it's anhydrous sulfuric acid, so it would immediately attack the water in your skin and everything.
Yeah, not a good place to be.
No.
Which explains why we haven't sent a lot of robot missions to the surface of Venus. It's just a very, very, very harsh environment.
And in fact, I think the old Soviet Union were the only ones who did it successfully.
Yeah. Now, there is talk of in the future doing that from the United States and others, of course, but right now the emphasis really has been on Mars.
Mars and the moon.
And the moon, right?
Yep.
And not so much anywhere else. Now, for the Ingenuity itself, it was sent up as an engineering test. This is the first time anybody has done such a thing. And it was designed to just fly up to 5 flights. And you look at the graphic that's on the left, kind of illustrates that. So it was going to fly 5 times. The actual number of flights that it made was 72.
Yep.
So way beyond any sort of, probably even when engineers were designing it, we'll go a lot more than 5 flights, but would anyone think they could do 72 flights with the thing? Probably not. The other thing it needs to do is have a line of communication with the rover, and the rover can then send that data back to Earth. It's not like there's a direct link, a comm link, communication link with Ingenuity, the helicopter, directly to Earth. So it has to be in such a position on the surface where the rover either can get there and have a direct link, or it's always, roughly in the field of view, so it can always send back the information back to Earth.
You mentioned something that I want to elaborate on too. You mentioned that this was a test case. It's because they are actually thinking of sending many of these things inside of another lander so that they can cover a lot more ground than even a rover could. So,
well, if you want to explore the surface of a planet and you can send up these miniature, tiny drone-like helicopters,
that's the way to do it.
What's to stop you with one? Send up 500 of them if you can afford
Absolutely. Yeah.
And you could have relay bases set up or have them in such a way that you can communicate and handle that data traffic. So there are ways to figure those things out. But that's the future for sure.
Absolutely.
So anywhere we can use that technology, like on bodies that have enough atmosphere.
Because, one of these things could fly around looking for interesting geology and sat down there.
In fact, NASA has approved a project called the Dragonfly mission to
That's
send,
Titan, right?
yeah, to go to Titan, and that has a thick atmosphere. In fact, we're going to have the Dragonfly going to be flying around. It's like a drone on Titan, unmanned drone, and so that is going to be spectacular.
That would. I hope I'm around to see it, please.
Well, I mean, we did have a lander on Titan.
We did. Huygens.
Yeah, so the Huygens mission, it was built by the European Space Agency, landed on Titan, and we have some images. You can find them on Google it. Images of what the surface of Titan looks like. And there's a nice video I noticed you can get on YouTube where it shows the actual images taken from radar as you're approaching to land on Titan, and you get closer and closer. And you can see what looks like dried up tributaries on the surface of Titan.
And lakes.
Yeah, so people speculate that there is even lakes of methane or hydrocarbons on the surface.
The neat thing that led to that is showing off some of my geology knows, is that they can see what are called alluvial fans. So this is where soil, if you will, or in this case ice, flowed due to some method and then reached a level place and fanned out. And you can see all kinds of these things, like in Death Valley and so forth, where water rushes down out of the mountains occasionally and produces these alluvial fans.
Now, I remember early data. I think it was from one of the Voyager mission as well, but definitely Cassini caught glimpses of sunlight glinting off the bright surface of Titan. That it's cloud covered, but they managed to get enough clear spot that they could see with the right filtering of the image camera. You see a bright spot which looked like we see on the Earth when you see sunlight reflected off the surface of a body like a lake or something.
Right.
So what is that object that caused that reflection? Is it a lake of some type of hydrocarbon?
Well, I was about to say, it's certainly not liquid water because water freezes as hard as granite rock at the temperatures on Titan.
So H2O will be ice, not water.
Yeah.
But, I mean, if it is hydrocarbons, maybe Titan is the new gas station of the solar system.
Absolutely, yeah. Maybe that's the fuel stop for the trip to Proxima Centauri.
Or to Uranus and Neptune, right?
Or Uranus
Who knows,
and Neptune,
right?
yeah.
So it'll be interesting to see what's there. And so that mission's coming up, I think, in 2030s is when it's due to land.
Okay.
So you just so that's another reason why you should eat well, is to be able to live long enough to see the results coming back from these incredible missions that's going to happen in the near future.
Absolutely.
Europa
Clipper.
Yeah, there's lots of stuff that's happening again. Now, getting back to Ingenuity itself, so it lasted for well over 2 hours in terms of total flight time, 128 minutes, 2 years on the surface, and the amount of distance that it had flown was about 11 miles. Now, the reason why we can put those numbers, why not 12? Why isn't it still going? Well, Robert, if you go to the next slide, unfortunately, this is why it was in the news recently, is that NASA lost contact with the helicopter at one point on one of its flight, and while it was still up in the air.
Right.
And eventually, when the rover moved to a place where it could have direct communication with Ingenuity and reestablish contact, they found it was sitting on the surface of Mars. That's a good thing. But what they discovered when there's a camera on board the helicopter itself, and this image that you're seeing there is the shadow of one of the blades. And if you look at the end of the shadow, it's clearly the blade has been damaged.
And keep in mind, it's spinning at 2,700 RPM. So that blade has to be balanced. Any damage like that means it can't spin. It'll sit there and vibrate and jerk the thing apart.
And there's been other images that you can look at also on Google if you like, search for it, and it shows the shadow of another propeller, and the end of that is also damaged.
Yeah.
In fact, if you look at the left of the shadow, you can see disturbed soil on Mars. That's because the blades hit the soil, what it looks like to me.
Chopped into it.
And that's obviously how the end of the blades got damaged. So the mission of Ingenuity is now over.
Yep.
But look what it accomplished, right?
Like Spirit and
far exceeded expectations, right?
I'll just point back to Spirit and Opportunity, the little missions that could.
Yeah, exactly. So this is a great achievement for engineering and space exploration, to be able to do what we did with Ingenuity, and that's really going to open up a whole new way of exploring bodies in our solar system going into the future.
Yep, I agree.
Now, the next big news that kind of happened related to astronomy and physics is, if you go to the next slide, Robert, is the unfortunate passing of Arno Penzias. Now, anyone familiar with astronomy, like talking about specifically of cosmology, the origin of our universe, the Big Bang, Arno Penzias was the co-discoverer, along with Robert Wilson, in the mid-1960s, of what today we call the cosmic microwave background. And what that really is if we have the interpretation correct, it is the leftover heat from the Big Bang.
Yep. It's where the curtain was pulled back and things got cool enough that hydrogen was no longer ionized.
Now, back in the 1950s, let's say, going into the 1960s, there was really two competing models to explain the origin of everything around us, the universe as a whole. One of them was the Big Bang Theory, and by the way, Robert, I think, isn't that the name of a TV show or something?
Yeah, that's the name of the
but I'm
TV
not
show.
sure. And the other thing, the other idea, is something that we call the steady state hypothesis, or
Yeah.
right. Now, back in the 1920s, it was discovered by Edwin Hubble, and others helped contribute to this discovery. It was discovered that the universe is in a state of expansion. The further away a galaxy is from us, the faster it's receding. And we know that because we can measure something called its redshift. And this gets the very simplest way of thinking about it is the Doppler effect. Just like, for example, if you hear cars pass you on a highway, if you're standing still, maybe you're fixing a flat or something on the side of the interstate, that you hear when a car is approaching you in the distance, a higher pitch, and then when it passes you, you hear that lowering of pitch, and then it's streaming away, and it has the lower pitch. You get the type of effect, almost like listening to NASCAR.
Yep.
How do you know if you're listening to NASCAR, Robert? Because you hear this, right? So
Yeah.
what is that? And that's exactly what it is this Doppler effect.
Right.
So when the sound of the engine is approaching you, the wavelengths are shorter than what they would be if the motor was stationary relative to you, the car, in
Right.
other words. And once it passes you, then the wavelengths, the sound waves, is longer, and we hear that with our ears, interpreted by the brain, as a lower pitch. Higher
Right.
pitch when it's approaching, lower pitch when it's receding from us. And that transition, that noise, is when it goes from high pitch to low pitch when it's passing us.
When it's passing it. Yep.
So the same thing occurs for light waves. When we watch a source of light like a galaxy, when it's moving in space relative to us, we can see if it's approaching or receding from us, if that's what it's doing, by measuring either the shortening of the wavelength or the lengthening of the wavelengths that we detect. So in this case, what we observe is essentially every galaxy beyond our very local neighborhood all displays a redshift. That means they're receding away from us.
Right.
Now, it's not like we're at the center of the recession of things. No matter what galaxy you were living in, you'd measure the same thing. The whole universe itself is expanding, carrying every galaxy away from each other.
I always try to tell people that it helps if you just think of space instead of space being nothing. Space is a box. It is something. It is an object you can change and meld and mold. So that helps some people grasp a little more what you're talking about.
So in the 1920s, we knew that the universe is expanding because that's been observed. And some of the and then from that, if someone tells you, well, the universe is expanding, then you immediately think, well, wait a minute. That means yesterday the universe must have been a little bit smaller than it is today.
Yes.
And that also means a year ago it was even smaller still. 10 years ago, even smaller. 100 years ago, 1,000 years ago. Well, then how far back in time do I go so that the universe was at a single point? That immediately begs those type of questions.
Mm-hmm.
That also means that there must have been a moment back in time, in the very simplest way of thinking about the expansion of the universe, where the universe had a beginning.
Yep.
And today, we estimate that moment back in time was about 13.8 billion years ago.
Right.
So since that moment, the universe has been expanding ever since. But what were the conditions like in the early universe? Well, imagine you take a container full of gas, okay, at a certain temperature, let's say for sake of argument, room temperature, and you have it isolated somewhere. So there's nothing outside of it, and that would be our universe analogy. And if you were to compress that container rapidly, what happens to that gas, Robert?
It heats up.
It heats
dramatically.
up. And what about the density of that gas?
It goes up too.
It increases. So the early universe, according to the Big Bang theory, if it's correct, and even if the very beginning of the universe, even if we don't nail down what happens there, we know for sure that if things were much closer together, the early universe had to be very dense and along with that, very hot. Now, since that early time, the universe has been expanding. One way to think about it is that heat from the early moment of the Big Bang has been filling up an ever larger volume of space. That causes the density to drop and also the temperature to
Drop.
yes. So it's been
You know,
going down ever since.
Bottom line, there's more space for that energy to be spread over.
Right. So then today, if the Big Bang theory is correct, today, everywhere around us, there should be this leftover quote unquote heat from the Big Bang.
That smeared out heat that I was just mentioning, yeah.
So today it's going to be an extremely low temperature because the universe has expanded enormously since the early moments of the beginning of the universe. So if you go back in time and you calculate, and if you had a way of probing it, for example, what is the temperature of the universe? It just increases and increases until eventually you're into billions of degrees. Okay? But then you can ask, then, what is the temperature now? Now you can do that calculation, and people have done that calculation, and you get a value close to what we call about 3 Kelvin.
Yeah.
Okay, 3 Kelvin. And that temperature is extremely low. That's about minus like 270 degrees Celsius, minus 400 and some Fahrenheit. That's even cold for Grand Forks standards in the middle of winter.
Oh yeah.
And
I wouldn't want to be in that, even with a good suit.
no, that's unsurvivable, that cold. But that would be the leftover heat from the Big Bang today. And what Arno Penzias did, along with Robert Wilson, is they discovered this leftover heat from the Big Bang.
Yep.
It is there.
And how do we know that's what it is? Because it's a black body curve with its peak at 3 Kelvin, at the temperature you would expect for a 3 Kelvin radiator.
Now, we measured it very accurately since the early 60s when it was first observed. But at the time, the competing model for the origin of our universe, the steady state idea, basically, the way to summarize it, the pure steady state version, would be that the way the universe is now is the way that it's always been, and the way it always will be going into the future for eternity.
Mm-hmm.
But that is not what we have when we note it in the 1920s that the universe is expanding. Because it's expanding, and remember, we observe that, it's not made up. The early universe looks different. It was denser and hotter than later on in the history of the universe. So the steady state model was not correct. So what the supporters of the steady state model did, and Fred Hoyle is sort of a major astronomer, if you know that name, who propagated this idea, is that, well, yes, the universe is expanding. That's observed. We can't get around that fact. So the steady state supporters said, but what happens is new matter gets created, if you like, in between the space of the old matter spreading apart. And so that overall, the density of matter never changes, ever.
Right.
But then you immediately ask, how do you spontaneously create this new matter? And the reply really was, if you boil it down, we don't know at the moment, but science is advancing all the time. We'll figure that out in the future.
Yep.
So that's how they got around it. But that type of model, the steady state model, does not include a very hot, dense phase to the early universe. Mm-hmm. So if there is this leftover heat from the Big Bang, that would essentially get rid of the steady state model.
Steady state model can't happen at that point then.
And so Arno Penzias, along with Robert Wilson, observed this leftover heat from the Big Bang. That was really the end of the steady state model for most people at the time. Yep. It went away. And
a few clung on to it, like Fred Hoyle.
Some people think the Earth is flat. Some people think we didn't go to the moon. There are always going to be a selected few that cherish these other ideas. Now, ever since this moment, though, the Big Bang theory has been the primary explanation that we have for the origin of our universe and its evolution afterwards.
Yep.
And so the major pillars of evidence today for the Big Bang include, number one, the leftover heat has been discovered. That's the cosmic microwave background. And by the way, Arno Penzias and Robert Wilson won the Nobel Prize in Physics in the mid-70s, I believe, for the discovery of the leftover heat from the Big Bang. The other evidence is the fact that the early universe looks very different than it does today. So if you want to know what the early universe looks like, you don't have to hypothesize or think about or sit around a table and dream up things. Just look at objects that are very far away. You're looking at them like they were back in the early history of our universe.
Right.
And we find the early universe looks different than it does today. Galaxies are more interacting, a lot more smaller galaxies, a lot more active galactic nuclei, a lot more star formation, a lot more irregular shaped galaxies, and so on. In fact, JWST observations have recently shown that is the case. It supports the Hubble Space Telescope images of those facts. The other thing that we use is to wonder then where did the light elements come from, like hydrogen? The first generation of stars formed from hydrogen. It's not like a prior generation existed that formed hydrogen. Hydrogen had to be there in order for stars to use that hydrogen to ultimately form helium and other elements. So where did that hydrogen come from? Well, you can explain that naturally. If the early universe was hot and dense, you can actually cook the hydrogen. In fact, hydrogen and helium, and then a very small trace amounts of some other things, were formed in the first roughly 3 minutes of the universe itself.
And in fact, the amounts of those can be predicted given what we know of physics. And guess what we find? Those amounts.
Yeah, exactly. And so the piece that all together, the four major pillars of the Big Bang is the universe is expanding, the leftover heat from the Big Bang, the fact that the early universe looks different than what it does today, it's evolving, and the other thing was the discovery of, the generation of the light elements, of the production of the light elements, as we say. Primordial nucleosynthesis is the fancy term for that.
And this is why I will say, come on, right now, I have to scoff a little bit anytime I hear somebody say, oh, there's no evidence for the Big Bang. Yeah, okay.
Now, to kind of say a little bit more about the significance of the discovery by Arno Penzias and Robert Wilson of the leftover heat from the Big Bang, to get a good view of this leftover heat, you want to get away from the interference due to our atmosphere. So put the measuring apparatus, if you like, instrumentation in space. And we did that. And the first good one, we sent up unmanned rockets and we sent up balloons. But the first good one to do it from space was the COBE mission. And those results then came out back in 1992. And on this slide, on the far, so what you're seeing here is an all-sky projection with contributions from the Milky Way has been removed. So you're seeing temperature fluctuations in the leftover heat from the Big Bang. But these temperature fluctuations have been adjusted to very, very high contrast so that you're seeing differences between hot and cold areas of 1 in about 100,000 or so in temperature fluctuations.
That's good resolution.
Very, very high resolution, very high contrast would be probably the best way of thinking about it. Very high contrast. Now, the section of the image by COBE on the far left shows you our resolution that we could do in the early 1990s. And you see blobs, right? And that blobs represent different temperatures. Now, the differences in the temperature, even though they're minute, reflects directly differences in density of matter. So what you can say is that the early universe, and you might ask, well, what do you mean by the early universe? This leftover heat that we're seeing here, this snapshot, is what the universe looked like about 400,000 years after the Big Bang. At that point, the universe has expanded enough that it's cooled down to about 3,000 Kelvin, and that's approximately the same number in Fahrenheit.
Right.
Okay? That now, energetically, electrons can bound up with protons to form neutral hydrogen atoms.
And that allows light to pass through.
Right, and because you're taking away a lot of the free electrons, and electrons love to interact with light, with photons, because you're bounding up the electrons inside of hydrogen atoms, that means that light, the leftover heat from the Big Bang, can more freely stream through the universe. And that's what you're seeing here. It's like looking at a fog bank in the distance. When you're inside the fog is all around you, of course. But if you're well outside the fog bank and you look towards the fog, you'd say, how far can I see? Well, you see that last scattering surface, the near side of the fog bank in which light last scattered amongst the water molecules inside the fog itself, and that's the edge, the near edge that you can see. That's analogous what we're seeing here.
Mm-hmm.
So we know that the universe, even just 400,000 years after its formation, had density fluctuation, differences. The density wasn't the same everywhere. That is a good thing, Robert.
We're here.
We're here. In other words, we needed regions in our universe that had slightly more matter than other places accumulated, so that gravity ultimately could collapse those objects and form galaxies, stars, planets,
and people.
And us.
We're a density fluctuation, folks.
So that was a good thing. So it was extremely important that we have a good measurement of this leftover heat from the Big Bang. Sort of in the middle, you see that's the second generation of telescopes we put in space to measure this leftover heat from the Big Bang. This is the WMAP, the Wilkinson Microwave Anisotropy Probe. How do you like that for regurgitating?
That's a mouthful.
How do you like that for regurgitating my memory banks?
Yep. All I can say is NASA loves its acronyms.
Exactly, and this is 2003, and we've done an even better, the Planck mission, which was mainly driven by the European Space Agency, and that's the data you see on the right, much higher resolution even more so than the last two. And this is data that was released, as you see there, in 2013. The last data, the final, if you like, dot the I's, cross all the T's, that was released in 2018. And from that information, we can say a lot about the universe. We get a very precise measurement of the age of the universe. It's about 13.8 billion years old, with a very small uncertainty on that. And we can even get a very good measurement of the expansion of the universe, which is a little less than 70 kilometers per second for every 1 megaparsec of space, which is a length equal to about 3.26 million light years. And we've talked a lot in previous podcasts.
Yep.
We can certainly do so in the future.
Yes.
And so this was, the death of Arno Penzias really, if you like, allows us to think back of the tremendous achievement. I don't like to be sad when people die because you can't help it. I like to celebrate what they did in their life.
Yes.
And to celebrate Arno Penzias along with Robert Wilson, who's still alive today, then is to go back and think about how significant the discovery of this cosmic microwave background is for all of humanity. It puts us intimately closer with the cosmos.
Yes. I love it.
Now, if you're interested in science, if you're interested in physics and astronomy and so on and so forth, please join us here at the University of North Dakota. We have classes available both online and on campus. So hopefully many of you who are kind of waffling, if you're in grade 11 or something and want to figure out what to do with life,
come join us.
Going into any type of field in higher education is the way to go. It doesn't always have to be science and technology and engineering and math. It can certainly be the arts and other things. We need science communicators, right?
Right.
We need to be able to demonstrate all of these wonderful things that we discover in science to get the layperson to understand, right?
We need people who can actually make some of these pretty pictures to represent what some of these data are meaning.
We need to bridge the gap.
We need to bridge that gap, yes.
Right, so it's very important. Now, our next podcast will be next Tuesday on February the 6th at the same time, 3 p.m. Central Standard Time. We always leave you with a quote.
Right.
And today's quote is a very famous quote by Isaac Newton.
Okay.
And here's this quote.
Which one?
Here you go. Robert's been waiting all day. I wouldn't tell him the quote, right?
He wouldn't tell me before.
Yeah. So here it is. I seem to have been only like a boy, playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me.
Woot.
Thank you very much for watching, and we'll see you next time.
We'll see you next time, folks.